Hey everyone, welcome back to my tutorial videos where I will be covering math tutoring videos. This video is for the squeeze theorem, which is a topic in AP Calculus, and it's in both AP, AB and BC. So what is the squeeze theorem? The squeeze theorem is just another way to find the limit of a function if your conventional means don't work, and you use this by comparing two other functions. So say the function you're trying to find the limit of is g of x, and there are two other functions, f of x and h of x, such that g of x is in between both of these. So something like this. For this, f of x and h of x have to have the same limit as at a certain point. So the limit of f of x as x approaches a must be equal to the limit of h of x as x approaches a, and say this is equal to some value L. So if both of these are equal, and they're both equal to the same value, then this means that the limit of g of x as x approaches a is also equal to L, because it is in between both of these. And if you have something like this, then there is only one possible value for g of x, which is just L. So to illustrate this, it might be helpful to draw a graph where the red function is the limit you're trying to find. So this is your red function, and say this is the point you want to find. And we'll just label this g of x. This function h of x has to be greater than g of x, but at some point a must approach this same point over here. Same with f of x, except f of x is less than g of x. So it looks something like this, where all three of these functions converge to the same value at a certain value of a, meaning that they all have the same limit. And since you know the limit for h of x and f of x, and they're equal, you can calculate the limit for g of x. So to start off with an example, say you have a function g of x, and it is in between x plus 2 and x squared. Find the limit of g of x as x approaches 2. So for this, you would want to find the limit of x plus 2 as x approaches 2, which would just be 2 plus 2, which is equal to 4. And the same with the right hand side. Again, instead of x plus 2, you use x squared, because that's this function over here. And then find this limit of x squared as x approaches 2, which is just 2 squared, which is also equal to 4. So you have 4 is less than or equal to g of x, is less than or equal to 4. And there is only one possible value that can fit this equation and still hold true, which is 4, because if you put 5 here, it'll be out of this bound. And if you put 3 here, it will also be out of these bounds. So the only value that will work here is 4. So the limit of g of x as x approaches 2 is equal to 4. So now for another function. Say g of x is in between, not e, 2 to the power of x and negative x over 2. So, negative x over 2. Find the limit of g of x as x approaches negative 1. So again, you would use this upper bound over here and this lower bound over there. So the limit of negative x over 2 as x approaches negative 1 is just equal to negative 1 over 2, which is 1/2. And if you take this right-hand side, if you take the limit of 2 to the power of x as x approaches negative 1, that would be 2 to the negative 1. And if you remember your exponent properties from algebra, a negative exponent is the same as having 2 to the 1 on the denominator. And since 2 to the 1 is just 2, you have a half again. So like before, you have 1/2 is less than or equal to g of x, which is less than or equal to a half. And again, like before, 1/2 is the only possible value. So the limit as x approaches negative 1 of g of x is a half. Sounds simple enough, right? It also works with infinite limits or even trig functions. So take the function x cubed sine x. Find the limit of this function as x approaches 0. So limit of g of x as x approaches 0. And now you might be thinking, I can just substitute 0 into this function and it will still work. Yeah, it does work in this case, but it is not the case like that for all trig functions. Which is why I will go through the squeeze method with this function anyways. So if you were to graph the sine graph, it always oscillates between negative 1 and 1. It never exceeds 1 or negative 1. And it goes like that for its entire domain, which is all real numbers. So you can write negative 1 is less than or equal to sine x is less than or equal to 1. And then, so now where does the x cubed come in? You can multiply all of these by x cubed. So multiplied by x cubed multiplied by x cubed, and I will also multiply this by x cubed. So now you get negative x cubed is less than or equal to x cubed sine x, which is less than or equal to x cubed. This looks more like a regular squeeze theorem setup. So now you find the lower bounds limit and the upper bounds limit. So as x approaches 0, negative x cubed would also approach 0 because 0 cubed is 0. And it's the same thing with x cubed. As x cubed approaches 0, this function will also approach 0. So you have 0 is less than or equal to x cubed sine x, which is less than or equal to 0. So the limit of x cubed sine x as x approaches 0 is equal to 0. And so you could have just substituted 0 into this function, but there are cases where that does not work. One of those cases being if you have an infinite limit. So if x is approaching infinity or negative infinity. So we'll take another well-known function, which is sine x over x, and find the infinite limit of that. Sine x over x, we were given that the limit of this function as x approaches 0 is 1. But what is it as x approaches infinity? Again, like before, we'll take sine x since that's on the numerator. And as we know, that has a range of negative 1 to 1. So if we were to multiply that by 1 over x, we would get negative 1 over x is less than or equal to sine x over x, which is less than or equal to 1 over x. So now we find the infinite limit of negative 1 over x and 1 over x. So for negative 1 over x, it would mean that the denominator is constantly getting bigger since x approaches infinity. But a larger denominator means that the actual fraction itself is smaller. So as your denominator keeps getting bigger, your numerator is the same. So the fraction itself is getting smaller and smaller and smaller until it reaches 0. So that means your infinite limit for 1 over x is equal to 0. And the sign you have over here does not change it, because this denominator is simply too big. So the limit of 1 over x as x approaches infinity is also equal to 0. So you have 0 is less than or equal to sine x over x, which is also less than or equal to 0. So your limit of sine x over x as x approaches infinity would also be equal to 0. So the squeeze theorem itself works, but it would just have to be continuous, or it should at least be defined at that certain point, because again, if the function is not continuous and is like a jump discontinuity, then the limit will not exist. Limits do exist if there are discontinuities, just only for a certain type of them. Anyways, thank you so much for watching, and please stay tuned for the next video.